So in this discussion, I want to talk about what you would see if you're looking at a finite impulse response filter, typically thought of as an FIR filter, thought of typically as a digital filter, so you're typically going to have some sort of continuous discrete conversion in front of it. And what does this sort of structure and implementation in front of it look like? Well, if I'm looking at this filter, it'll probably have some coefficients H or some coefficients B sub n, which I would, when I convolve it together, I will get this type of response where I'll have a whole sequence of coefficients and then a number of delayed sort of inputs. And that's often thought about in terms of, say, unit delay functions. There's a number of ways to approach this approach, to think about it conceptually. But what is it physically going on here and when you're actually building it? And thinking about it kind of pulled together if I was building a custom digital implementation. Practically, in many cases, you're writing computer code to do the same thing. But either way, the picture is important in terms of what you're building. And so if I'm starting with a particular input, the first thing you notice is that there's a whole set of delay lines. Why? Well, if you notice that I need to create a whole bunch of the inputs and it's delayed various inputs, I need to be able to find a way to create all of those. Well, I'm going to do this as delay. Well, the interesting thing digitally is this is simply a register, a memory, a way to maybe just a simple shift register to take the register bits here and then just move them over here. And this is one of those things, if you've gotten to do any digital implementation, you know it's one of the most straightforward things and one of the most natural things to be doing with digital circuits. Natural aspect with all the latching behavior and so forth. And so as a result, you can look at this whole structure and go, I create all the delay lines. Well, the next thing I need to do if I'm looking at this level of implementation, either spelled out as a whole bunch of, may see as a whole bunch of coefficients, is I need to create the coefficients, B0 to B sub m. And I need to multiply those values together. So that's the next thing that's going to happen here. So I'm going to look at this multiplication in this entire function. And then the last thing I'm going to do is take all of that and then add all of those things together, which is going to be the inputs and the delayed inputs all multiplied together. And then when I'm done with that, I'm actually going to get the output. And that will give you your nice sort of convolutional output. You might actually want to think about this in a Z-transform domain. Why would you think about it that way? Well, you might imagine that each of these delays is a Z minus 1, which is actually a unit delay. So you'll see all of these things used in different places and different spaces. Excellent. So this is how you get a single output. If I want to get multiple outputs, I need to repeat this pattern. I might keep the delay for everybody, but then I need to multiply that vector against a whole set of a vector of coefficients and then add that together. Well, if you think about that for a moment, that's actually multiplying a vector times a matrix. And so that would be a vector matrix multiplication, where I have a whole delay line where I take the input and all of its delays, and I take all of those and I put those into a straightforward computation, which is going to say, let me take all of those delayed inputs, which is really that input vector, times a whole bunch of weights to create a whole vector of outputs. And again, if I'm going to now call it a vector, it will now use a vector notation, which is why it's a bold letter on there. And this works very well. And what you're going to find is that this vector matrix multiplication, because I'm often going to want to have an input going to a vector of outputs and a number of things, I'm going to see this and some of its other linear algebra correlates of it, including tensors and so forth, almost always showing up in computation. And so this becomes sort of that main computation that you see. I mean, if you look at machine learning, it's going to be the main thing you run into. You will see this in many places. Now, some people might go, well, do I need to just do a delay line, or could I do other things? And the answer is certainly. I could imagine actually building a range of filters up front before doing this, and sometimes that has some advantages depending on the medium that I'm working with. And particularly if I'm dealing with these inputs may be originally coming from an x of t, I might decompose them before I go to my continuous to digital conversion, which might also give some improvement over what this process looks like or other aspects. And so this works out quite nicely. Now there's probably sitting an interesting question to think about, which is to say, well, could I eventually imagine just going from x of t to y sub t from here to here, and without having to do this continuous to digital conversion and maybe do all of this in a more analog form? And that would be a really intriguing question, and one that would be fun to address, one that you can do, and one that there is actually a lot of interest in asking these questions. But that being said, this is the typical way that you're going to look at for an FIR implementation. Now, there's other ways to do IIR type of structures where you have feedback, but this is the way you would typically imagine this type of an implementation.